So some students have asked me for the following information, which is this one, the schedule for the videos that you are supposed to watch. I made this schedule, but it is totally up to you. But you should finish chapter 7 by week 10, so that on the Monday of week 11, we can do the quiz for these few topics. Then on 11, 12, 13, we'll do eigenvectors and eigenvalues. This is the suggested speed. You can ignore 8.5 A, B onwards, 8.16, 8.17, and then 9.1. You have about 3/4 or 4/8 of a question in this, and about 1.2 questions in chapter 6 and 7 in the exam. And in the exams, we will cover at least how we do things in the tutorial and in the quiz. So the quiz will give you a good guideline on what we're going to do for the exams. So now I'm going to do tutorial. This is 6, I guess. Question 4 first. We have two vectors, y and u in R2, and we are going to project y onto u. And you notice this word, orthogonal projection. So we are going to study what is orthogonal projection first. Right, the answer is here. So we have 7 and 6 for y. So this is the Cartesian coordinate. This is the x-axis, the typical x-axis, or sometimes we call it the horizontal axis. And now it's confusing because I have x and y, and then, so let's call this the horizontal axis and the vertical axis. And of course, as you know, the first element is the horizontal axis and the second element is for the vertical axis. Now, the important thing to note is that these two axes are right angled to each other. So we call it the Cartesian axis. And we have y for 7 and 6. So this is y. And the first entry is 7. So the horizontal entry is 7. And the vertical entry is 6. And then we have a vector here. So this is y. Now we want to project y onto u. So we have to draw y and u. And u is 4, 2. So here is 1, 2, 3, 4. This is 4. And this is 2. And now I use different color for yu. And I'm going to project y onto u. Now, first is we want to draw a dashed line here, extending u. And then the idea of orthogonal projection is basically this. So you take a torchlight here. This is your torch, and you shine your light behind y. This is the y vector, and which is orthogonal. Okay, that means it is perpendicular to u. And the shadow that is being cast, so I'm going to cast a shadow here of y onto u is projection of y onto u. And that's the key idea. And this interpretation, of course, is the geometric interpretation. You will hear two words, the geometric and the algebraic representation. This is a geometric representation. You can see it. You can see the vectors, and you can see what this orthogonal projection means. Later on, when we're calculating, of course, we're using the algebraic equations to solve this. The green is the u, and the red is the projection of y onto u. So, projection of y onto u is a vector, and it's a vector pointing the same direction as u. So that's the 2 fact. However, its length is dependent on, of course, y. If y is long, then the shadow is long. It is also dependent on theta, the angle between the two guys. So one of the interesting thing about orthogonal projection is this. So I'm going to draw this now. Imagine this is u, and now y is, this is y. This is a right angle. And if you shine a light here, and because y is already right angle to u, the shadow, there is no shadow being cast onto u by y. So the orthogonal projection in this case is 0. So later on, you realize that when the vectors are orthogonal with each other, the projection of that vector to the other one is 0. So the equation for projection of y into u, you have to memorize. And please be careful. Sometimes I say A into B. Sometimes I would say U into V. It doesn't matter. You just change the appropriate variable. Okay, so, but in this example of y onto u is always y dot u dot u in the denominator, and this guy is a scalar. This guy is a vector. And then what we see again is that it is a vector in the direction of u scaled by this vector. So after a while, you'll be asking, you have to be reminding yourself what is y dot u in the simplest case. In this case, when our vectors are nothing but column vectors, y dot u equals to u dot y equals to y transpose u equals to u transpose y, whichever you prefer, doesn't matter. So there are so many ways to calculate this. So I choose y transpose u in this example. And the answer is 7 multiplied by 4, 6 multiplied by 2. What's my answer? 7.4 is 28. 28 plus 12 is 40. So the numerator is 40. What about u dot u? You must be very careful with u dot u. In some of the equations, I would tell you the denominator is u dot u. But what is the u dot u? It is the norm of u square. Okay, so it doesn't matter. And what is norm of u? Is equals to the length of u square. Okay, so all these notations are equivalent. And it will cause some problems to students when the notation change. But you have to try to remember. So u dot u, what's u dot u again? U is 4, 2, 4, 2. So at the end, it becomes 16 plus 4, answer is 20. So we work throughout. The numerator divided by denominator is 2. U is 4, 2. So answer is 8, 4. We can go and plot this here. 8 here and 4 here. So if you go through all this computation, you realize that we land up a point. This is the projection of y onto u. And you realize that there is no other way along u that I can get closer to y. So the theorem is very important. The orthogonal projection projects y onto u, giving us a point on u that is closest to y. Intuitively, you can think of this. As I move away, if this is my y1, then you realize that this is the distance from y1 to y. If I move the other way, maybe I stop here at the pink one, then this is the distance from y, for example, y2 to the required y. All these distances that is not perpendicular to this point is further away because it becomes the hypotenuse of the right angle triangle. So that was the proof that we show and shared in the lectures. We want now to check that E, this vector E, is nothing but this guy, which is projection of y on u plus E would result in y. So we have this equation, y equals to projection of y onto u plus E. Therefore, E is equals to y minus projection of y onto u. And because we know the value of y, we know the value of projection, therefore we can calculate E vectors. So E is minus 1, 2. How do I know? Actually, all you need to do is, this is the vector, and you will go to minus 1 on one side and 2 on top. Okay. From the graph, it says that E is orthogonal to this guy. How do I prove? So again, if E is orthogonal to this vector, all we need to do is to check by doing the dot product. If the dot product is equals to 0, then it implies that E is the right angle to the projection of Y onto U. So we calculate by brute force and we get this. And now we know that E is orthogonal to the projection of Y onto U. Let's continue this diagram. It is obvious that this vector plus E is equals to Y and that they are right angle to each other. So we call such a thing, we say we decompose Y into two vectors, orthogonal decomposition. So 7, 6 is equals to Y hat. This is Y hat plus E. Then again, we check and then it's correct. Why is this equation true? Right? How did we find an equation that is dot product on the top, dot product on the below, multiplying by U to get this?
And a vector A, okay? And then let's find the geometric projection, and we'll call it P. Okay? Let's try to express P in terms of A and B and throw the kitchen sink at it, meaning you're allowed to use whatever you want. Lengths, angles, whatever you want. You're allowed to use. All I'm requiring is that you express P in terms of A and B. So what direction does P point in? Yeah, it points in the direction of B. So whatever it is that we'll get will be proportional to B. So it'll be some number times B. You agree? Okay, step in the right direction. Okay, that's very nice. What number? Well, let's see. What is the length of P? So just answer that question. I see lots of volunteers for other things. You have the length of P? Yeah. Okay, gamma. So we'll call it gamma. So the length of P is the length of A times cosine of this angle. You agree with me?
Right, guys, this one is the standard, yeah? As in cosine gamma is adjacent over hypotenuse in a right angle triangle. That's all. So if you evaluate adjacent, therefore it is hypotenuse times cosine gamma.
Remember that from projection from the right triangle, how sines and cosines work? Is this?
Now he called this the length of A, the length, the physical length of A, cosine gamma. So it is this length. Cosine is adjacent over hypotenuse. So it's adjacent this length divided by this length.
Is this correct? No, it's not correct. It's the wrong length. Because this expression, this vector that I have right here, has the length, whatever this number is, times the length of B.
Yeah.
And we want it to be this number. So what do we have to divide by? You have to divide it by the length of B.
Now, this is a very tricky point, guys. It is, you see, this is a physical scalar value. And B is not a unit vector. It can be a very long vector. So it will be this length times B. And if B is very big, so imagine, for example, B reaches here and this length is 2, then it will be 2 times B, so you'll reach here. So we must have a normalized unit vector pointing in the direction of B. And to get that, it is B divided by the norm of B to get a unit length vector pointing in the direction of B.
You guys are with me? Now it's correct. Let's see. Let's make sure it's correct. Where does this vector point? In the direction of B, right? Because it's proportional to B. You guys are with me? Are you enjoying this geometric discussion? Because we're in the geometric space. It seems like we're going in the wrong direction for discovering something that applies to polynomials and Rn. Okay. But remember my claim that this is such an ingenious combination that everything can be expressed through this combination. And I'm not quite seeing that combination here. But can I artificially put it there? Like, what's missing on top from having this combination? So I'm just going to put it in. You guys are okay with that? So I will multiply the top by length of b, and I'll multiply the bottom by length of b. Just as an artificial step to get it to this. I'm telling you, this is very artificial. It's so artificial, it ends up being perfectly natural.
Yeah, so he just introduced length of b on top, length of b below. So this cancels, of course, to be 1. But what he gets is length a cosine gamma length b, which is exactly what is a dot b. So you can now write a dot b on top.
Did something good happen? Yes, because what is this combination on top? Hey, it's a dot b. Step in the right direction, no doubt. And what do I have on the bottom? The length of b squared. But that's not good enough for me because I want to have nothing but dot products. I don't want to make a reference to length. The whole claim here is that if you have this combination, if you can evaluate nothing but this combination, plus addition and multiplication by scalar, then I can express anything geometric. That's the claim. So I don't want to say length of b squared. I want to go away from that. I just want to end up with this. Yes, Guru? Is it b dot b? Well, you say yeah. What about everybody else? Is it b dot b? Well, let's think about it. What is b dot b? B dot b is the length of b times the length of b times the angle between b and b. What is cosine of the angle? What is the angle between b and b? 0. And what's the cosine of 0? 1. So when you dot something with itself, it just equals length squared. So this is b dot b. And there we go. We have conquered one task. Find.
Right. So when we get this is exactly our equations that we show in our lecture notes. Sometimes we're lazy, or we will call it length of b squared, or sometimes norm of b squared. So that's the problem. You guys see 3 different equations, 1, 2, and then length of b squared. So some students are confused. So don't be. Maybe this is the easiest way to remember this. This is the most direct way.
The projection. On the right-hand side there, you have no lengths. You have no angles. You just have inner products.
Now, the word inner product is a generalization. So in your case, of course, in our case, we say dot product, but we can still say inner product. It's not a problem, really. Inner product is a generalization of the dot product.
And so this absolutely meaningless combination, by all accounts, not by all, by initial impression, completely meaningless, represents nothing. Like, they're kind of echoes of some things in there, but really nothing. All of a sudden, you say, oh, okay, I see that it's convenient. If I were a computer scientist, who's a computer scientist? Raise your hands. Okay, this would be a convenient function to have, dot. Because I would only have to call that function to find the projection.
Yeah, I think that was a very cool insight. So if we can write dot product, which is nothing but B transpose B, or you computer guys will write a for loop to multiply elements together, then we can write a function we call here, the same function is called here, multiplied by this. That's what he's talking about. Now, the other observation, which I want you to see now very clearly, is this. B dot B is painful to compute when B is not equals to 1. But what happens if the length of the vector B is 1? Then 1 times 1 is 1. So this guy we do not even need to compute. So if we have been provided with a vector b that is normal length, means length of 1, then this guy disappear because it's 1 times 1. Length is 1. So we later on you realize that we are going to ask you to do projection onto normal vectors, length of unit 1 vectors. Or if b is not 1, length 1, we're going to make b into length 1 first, and then we project so that we can get rid of this guy at the bottom. Okay, so let's come back. Okay, so we are done with this. Now, the second question that we want to attempt to answer is question number 7. So this is almost the same question. It says, let's project y onto u or onto 2u. And is there a difference? And of course, you look at the diagram, and in this R2 case, it is obvious that there is no difference whatsoever, because this is the answer. Projection of y onto u or projection of y onto 2u lands in the same point, because all we are doing is that we are shining our torch here. This torch is right perpendicular to u, and whether it is 1u or 2u doesn't matter. So where did that 1 and 2 disappear? Why did it does not matter whether it was 1u or 2u? So let's see. All right. So remember that we have this equation here. Whether if this is 1u, we just use 1u all over the place. And then if it is 2u, well, let's generalize. C is a constant belonging to the real number. U is the vector belonging to the space that we are interested in. And the top is y dot with cu. The bottom is cu dotting with cu multiplied by cu. So you have to do all these properties of the dot product, and we can bring the constant out. And then we get c squared. We can also bring the constant out. We have another constant here. So remember, this guy cancels. So this is back to exactly this guy. And therefore, we show that projecting y onto u, cu, or anything, or unit vector, you land at the same place. So it doesn't matter. All right. So now I'm going to discuss another question, question number 8. First, again, I'm doing the same thing, projecting y onto, then now it's not u anymore. W is a space, it's a vector space. Actually, projecting y onto u is also a vector space, but u, the vector space of u is very simple. It is nothing but that line, u running up and down, that's it. Okay, so the vector space of a single vector is very simple. It is just a line. Now, I give you 2u, u1 and u2, which are these two vectors. And w is now the vector space. I want to project y onto a vector space spanned by two vectors. So what does that mean? Right. So this is 6.2.5 orthogonal projection. The question is asking you to project y onto w. And w is still a vector space, but this vector space is now no more a single line. In this case, I draw a plane. So this is, of course, just a concept, but it means that any linear combinations of the two bases in W spans this space. And what is projection of y onto W is this. Again, it is an orthogonal projection. You will shine a light on top, and then this shadow will be cast onto the plane of W, the space of W. But where do you put this light source? The light source must be perpendicular to W. That's the whole idea. and then y would fall onto the plane of W, making this an orthogonal projection. The shadow cast onto here is the nearest point. Y hat is the nearest point to Y. That's the cool idea about orthogonal projection. So here it is Y hat, and here is the error. He called the error Z here. Sometimes it's E. So it doesn't matter. It is Y hat plus Z equals to Y. So you look at this equation. You bring the Y hat, the other side is Y hat plus Z equals to Y. Now, in our kind of courses, if this is Y, the approximation of Y is typically with a caret called the hat, Y hat. The approximation of Y in the subspace of W, in this case is Y hat, is projection of Y onto space of W. Now, this is the cool thing. If you forget about the other guys, if you ignore, so if you just look at this, isn't this exactly what we have done just now on U1? We project Y onto U1 divided by U1 dot U1 times U1. Because we are given two bases, we are given two vectors, and these two vectors are orthogonal. We are given later on U2, Y dot U2 divided by U2 dot U2 times U2. Because U1, U2, U3 are orthogonal, we can do this decomposition. The proof is here, but that's the cool idea. It means that we can just simply find Y along each of these U1, U2, U3, and then we can add it up. Okay, maybe I would show you this diagram. This is what I mean by adding it up. I have Y in the R3 space. I have U1, U2, I'm supposed to have U3. However, let me only reconstruct, okay? Let us try to reconstruct Y using only U1 and U2. In this case, if I only have U1 and U2, all I can do is to run along this space between U1 and U2, which is the horizontal plane. There's no way I can get a linear combinations outside this horizontal plane because I can't go up to U1. All I can do is run around this U1, U2 space. The nearest point that I can get to Y, and you realize is this point. But what is this point? It is a very nice point which says that all I need to do is travel along U1 to reach Y1 hat, which is this guy. And then when I finish with that, I travel along Y2 hat, which is this guy. So Y hat, which is this point here, is nothing but first traveling along Y1 hat, then reach Y2 hat. Or if you prefer, you travel along Y2 hat first, and then travel along Y1 hat. The computation of Y1 hat and Y2 hat is trivial because, in this case, you can just calculate Y with dotting with U1 and the rest of it, or projecting Y onto U1 first, then projecting Y onto U2. So the orthogonal decomposition is a very nice example of why we like something called the orthogonal basis. So go through this question well. This is quite important.